In this video, I am focused on accelerated motion. This is the third of 7 videos in my Unit 2 titled Kinematics. If you want to practice what is covered in this video, then check out the video description. You can find a link to my worksheet 2.03 as well as video answers for each problem. What is accelerated motion? We are looking for an object that changes its velocity over a time interval, and there are 3 main ways that an object might do that. The first is when the object speeds up. The second is when the object slows down, and the third is when the object changes direction, which changes the sign of the velocity, in this example from positive to negative. Now in this video, I am only focused on the first 2 of these, and we will revisit accelerated motion for changing directions later in the curriculum. Let's look at an object that is accelerating. Here we have a cart released from rest at the top of this angled ramp. I expect the cart to speed up, starting at a position of 0 meters, and approaching a position of 6 meters. In the data table, I am tracking the position of the cart every second, from 0 seconds to 3 seconds. 2 of the position values are known. The cart starts at a position of 0 meters, and 1 second later, the cart has moved 1 meter along the ramp slope. The question is, what might be the data points for the missing 2 boxes in the position column? Well, the cart has moved 1 meter in the first second. Because the object is speeding up, I expect the cart to move a length greater than 1 meter in the next second. So from 1 to 2 seconds, I'll say the cart has moved 2 meters, and I'll say that it reaches a position of 3. Well, the cart is still speeding up. So in the next second, from 2 to 3 seconds, I think the cart should move an even greater length. I'll choose 3 meters. So now the cart has reached a position of 6 meters, moving from 3 to 6. So when objects speed up or slow down, they should be changing their position at a non-constant rate. Let's look at a position versus time graph that tracks the motion of the same cart. This cart moved 1 meter in the first second, 2 meters in the next second, and 3 meters in the last second. So this is showing the cart speeding up, but in reality, this cart didn't move with just 3 different constant velocities on its way down the ramp. This was on a constantly sloped ramp. The cart was always speeding up, and so treat the current graph as an outline, and we'll want to fill in a curving line to explain the actual motion. A curve on a position versus time graph shows acceleration. Remember that the slope of a position versus time graph represents the velocity of the object, and so since this slope is getting steeper over time, that would indicate an object that is constantly speeding up. Let's look at a second example. Here we have another cart that is released from rest at the top of an angled ramp. I expect this cart to speed up as well, but now it starts at a position of 6 meters and moves backwards towards a position of 0 meters. I think the graph shape would look like this. We now have a y-intercept at the 6 meter point, and we end at a position of 0. Remember that the slope is related to how fast the car is going. This slope is getting steeper over time. That would show that the cart is getting faster over time. It is now just doing so in the opposite direction. Here we have a third example. The cart is back to starting at a position of 0 meters, but now it is given an initial velocity and is moving uphill. I expect this cart to be slowing down as it approaches the position of 6 meters. I think the graph shape would look like this. We have a y-intercept of 0 again, and the final position is 6 meters. Since the slope represents velocity, and this object is slowing down, I expect the slope to be getting less steep over time. The last example would be another cart given an initial velocity at the base of an inclined ramp. This object will be slowing down, starting at a position of 6 meters and moving in the negative direction towards a position of 0 meters. I think the graph shape would look like this. We have a y-intercept at the 6 meter point, and the cart ends at a position of 0 meters. The slope represents velocity. This object is slowing down, so I expect the slope to be getting less steep over time. When it comes to analyzing curves on position versus time graphs, I think you want to be really good at answering 2 questions. The first question, does the graph show an object that is speeding up or slowing down? And the second question, does the graph show an object that is moving forward or backward? For speeding up and slowing down, you want to look at the slope. Is the slope getting steeper over time? That would show an object that is speeding up. Is the slope getting less steep over time? That would show an object that is slowing down. For forward and backward, now we want to look at which way the line trends. This line starts low and ends high. This line is trending upward. That would be an object that is moving in the positive direction or moving forward. This line starts high and ends low. It is trending downward. that would show an object moving in the negative direction or moving backward. Next, let's look at velocity versus time graphs for accelerated motion. We're back to analyzing the cart released from rest at the position of 0, and it speeds up towards a position of 6. In graphing velocity versus time, this cart would start with a velocity of 0, being that it was released from rest, so the first data point is at the origin. Halfway down the ramp, the cart is now in motion. It is moving in the positive direction, so the data is now somewhere in the positive quadrant. And at the bottom of the ramp, the cart is moving even faster, so we increase the velocity on the graph again. Because this ramp has a constant slope, I expect the cart to increase its velocity at a consistent rate, and so this graph of velocity versus time should be linear. I made up some data to support the graph. Notice that the velocity is increasing at a constant rate, and now I can try to use the data to write a mathematical model that describes the relationship between velocity and time for the cart. This is a linear graph, so I will start with the slope-intercept form. The y variable is velocity, the x variable is time, the slope comes out to 1.5 meters per second squared, and the y-intercept is 0 meters per second. But what do these numbers mean? Let's see if we can figure out what the slope of 1.5 and the y-intercept of 0 both represent. To get there, let's look at two different scenarios. The first shows two carts that are placed on identical ramps. The difference between them is that the red cart is released from rest, while the blue cart starts with a velocity aimed down the ramp. In trying to graph both of these motions on the same velocity versus time graph, I think a difference would be their y-intercepts. The red cart starts from rest, so its velocity begins at 0. The y-intercept will be at the origin. The blue cart starts with some velocity in the positive direction, so its y-intercept will be somewhere in the positive quadrant. But after the initial point, these carts are moving down identical ramps. I expect them to increase their velocity at identical rates, so the slopes of these lines will be equal. The second example shows carts that are placed on different ramps. They are both released from rest, but the red cart moves down a ramp that isn't very steep, while the blue cart moves down a ramp that is much steeper. In graphing the motion of these two on the same velocity time graph, I think they would have the same y-intercept. They both start with a velocity of 0, so their graph lines would start at the origin. But from that point forward, since the blue cart is on a steeper ramp, it should increase its velocity at a faster rate than the red cart, so the slope for the blue cart is greater than the slope for the red cart. Back to the mathematical model from earlier, I think I can now conclude that the slope is equal to the acceleration. It is measured in meters per second squared, and it represents the rate of change in the object's velocity. The y-intercept is equal to the initial velocity. It is measured in meters per second, and it represents the value of velocity at the beginning of the problem, or when time was equal to 0 seconds. Let's summarize what we currently know about velocity versus time graphs. The y-intercept represents the initial velocity, the area underneath the data represents the displacement, and the slope represents the acceleration. Here are 4 different velocity versus time graphs that all show objects that are changing their velocity or objects that are accelerating, and the goal here is to draw the corresponding acceleration versus time graph that matches each of the 4 velocity graphs. Remember that for velocity graphs, the slope represents the acceleration. So for scenario A, we have a constant positive slope, so we should graph a constant positive acceleration. Graph B is a constant negative slope, so a constant negative acceleration. C, another constant positive acceleration, and D, another constant negative acceleration. In Physics 1 classes, accelerations are almost always constant in magnitude. If the acceleration is changing its value over time, that would connect to calculus, and that is likely not in a Physics 1 course. When it comes to analyzing velocity versus time graphs for accelerated motion, I think you want to be great at the same 2 questions from earlier. The difference between speeding up versus slowing down should be how the line behaves relative to 0 meters per second. The slowest an object can go is when it is at rest or at the origin. This line is getting further from the origin. That should show an object speeding up. If the line is approaching the origin, that would be approaching a value of 0 meters per second. That would show an object slowing down. For forward versus backward, we should be looking at which quadrant the data is in. If it's in the upper quadrant, those are all positive velocities. That would show an object moving in the positive direction or moving forward. And if the data is in the lower quadrant, those are all negative velocities. that would show an object moving in the negative direction or moving backward. The last piece of information to cover is an incorrect statement that I hear from many students. Students often think that if an object has a positive acceleration, then the object is speeding up. Well, here is a graph from earlier that shows an object with a positive acceleration because the slope is positive, but this data is approaching the origin, or a velocity of 0, so this object is slowing down, and this graph would ruin the statement from above. So what is a positive acceleration? That just means the velocity is becoming more positive. A negative acceleration means that the velocity is becoming more negative. Although these velocities in the graph would all be negative, notice that they are becoming more positive every second, and that's why this represents a positive acceleration. Let's end with an example problem. Here we have a velocity versus time graph that is showing the motion of a cart, and we are asked 4 questions about it. If you want to pause the video and try this problem on your own, resume when you are ready, and I will talk you through the 4 solutions. For question A, the object is slowing down. This is because the data is approaching the origin, or a velocity of 0 meters per second. Question B, this object is moving in the positive direction since the data is in the positive quadrant, using all positive velocity values. To draw the corresponding position versus time graph, let's use the answers to the 2 previous questions. What would a position versus time graph look like that shows an object slowing down and moving in the positive direction? Well, I want to see a line where the slope is getting less steep, that would show slowing down, and I want to see a line that is trending upwards, that would show moving in the positive direction. And when drawing an acceleration versus time graph, let's look at the slope of the velocity graph, which is a constant negative slope, and therefore a constant negative acceleration. If you found this video helpful, then please consider hitting the like button and subscribing to my channel. You will help me reach more students. For more content videos, tutoring information, practice materials, and live review sessions, check out my website or follow me on my social media platforms.